divergence test is the following, that if the limit as n goes to infinity of these terms is not equal to 0 or does not exist, then this series does not converge. And that's just a rewriting of the following theorem, which is what we discussed on Friday, that if the series converges, then the limit as n goes to infinity, an is equal to 0. So this theorem is the same as what I just wrote up there. It's just a rephrasing of it. So logically, if we have this statement here is statement A, and this is statement B, then what we've written here is that A implies B. And it's basic logic that if you have that A implies B, that means not B implies not A. So I don't know how to write that. So not B implies not A. And what this is not B. So not B is that the limit either is not equal to 0 or does not exist, implies not A. Not A is that this thing does not converge. So hopefully you have all studied a little bit of logic. So not B implies not A. And you know that this is a true fact. It's called the contrapositive. So this is the same as this. The divergence test is the same as this theorem. Okay? But in this form, it's more immediately applicable to us because we can look directly at the terms of the series to see what happens to the limit and then conclude something from it. Okay? All right. If we look at this, though, look at this statement. So if the series converges, then this goes down to 0. So I suggested you think about this as taking a sequence of steps. If we consider the special case when A and are positive, so we take a sequence of steps, and if we take this infinite sequence of steps, the only way that ends up being a finite quantity is if the step sizes go down to 0. Okay, and that should seem fairly reasonable when you think about it. Look back at the discussion in the video, Friday's video, if you're not sure. All right, what about just the straightforward reverse? Is it the case that if these terms goes down to 0, that it implies that the series converges? Is that true? Is that true? Is it the case that if we have a sequence of terms an, which go down to 0, does it imply that the series converges? Perfect. Yep. Note. The converse is not true. For example, an equals 1 over n. These things go down to 0, obviously. Yeah? And an goes to 0, but as we've learned well, does not converge. Okay, so the fact that statement A implies statement B does not necessarily mean B implies A. And for some people, that's a kind of a new thing. I mean, I've encountered had discussions with people who believe that A implied B means the same as B implies A, which is obvious, which is not. A implies B does not logically mean that B implies A. Yeah. All human beings walk on 2 legs does not mean that everything on 2 legs is a human being, right? I mean, ostrich walks on 2 legs, right? So the statement that human implies walking on two legs does not reverse and mean that two legs implies being human. Yeah? Yeah? So this is an example. We have that statement A implies B, but B does not imply A. Yeah? However, not B does imply not A. The contrapositive is true. All right, so these questions on the practice test include an increasing number of conceptual questions. As I told you in the introductory video, we are moving you more and more away from learning algorithms and more into understanding concepts. And there's a bunch of questions here on the practice test that are about testing your understanding of concepts. And one of the first things they test is do you understand that this theorem is not reversible? That going down to zero does not imply that the thing converges. So hopefully you're all clear on this because of this example, because you know that the statement A implies B does not mean that B implies A. Is this clear to everybody? Give me a thumbs up or a thumbs down. Give me some feedback. Okay, good. All right, so let's do question 9. The question is, which is always true? So which of the following statements is always true? Statement 1, that the limit as n goes to infinity, an equals 0, implies the sum n equals 1 to infinity, an converges. This is exactly what we've just been discussing, and the answer is no, this is not always true because of this example, right? It's sometimes true. If this was an was 1 over n squared, then sure enough, 1 over n squared does go to 0 and it does converge, as you'll later see. But it is not always true that if these terms go down to 0, the thing converges. So this is not the statement that is always true. Okay, so I'm going to do a cross like this, because this is not the statement that's always true. Yeah? Cool, let's write another one. What about this? Oh, which of the following statements is not always true? So this one is not always true. So maybe I should put this one. This is not always true. Okay, the next statement is the reverse. So the sum an 1 to infinity converges implies that the limit as n goes to infinity, an is equal to 0. Is this always true? Is this always true? Come on. Yeah, that's just the statement. That's just the theorem up here. So yes, always true. Next statement. If the limit as n goes to infinity, an is not equal to 0, this implies that the series diverges. Is this always true? Someone else, is this always true? Yeah, that's again, that's the divergence test. So always true. And the final statement is that if we have the sum from n is equal to 10 to infinity, an converges. This implies that the sum from n equals 0 to infinity, an converges. Is this always true? Why is that true? Yeah. Can you be a bit more precise about it? Can you give me some more details about it? Yep. The sum from n equals 10 to infinity of an converges implies that the sum from n equals 0 to infinity converges. Good. Yeah, so what does it mean? So I think all of you had the right idea, but let's try and express it in the language of maths, right? So what does it mean for this thing to converge? Capital N, like this. And what is this? This is limit as n goes to infinity of the sum from n is equal to 0 to 9 of an plus the sum from n equals 10 to capital N of an like this. Yeah? We're just breaking up the sum from n equals 0 to capital N into n equals 0 to 9, and then from 10 to capital N. Yeah? Where n is some big number, much bigger than 10, obviously. Yeah? But then this thing right here is independent of capital N. It's just a number now. It's just a number. Yeah? So that thing is just equal to this thing. So it's not depending on capital N again. It's just a number. N equals 0 to capital 9 an plus the limit as capital N goes to infinity of the sum n equals 10 to capital N an. Yeah? Are you with me here? Yeah? Give me the thumbs up or the icon. Or the thumbs down. Okay, looks good. Yeah? And then this thing does exist because that's what's given to us. That's this assumption here, right? So this exists. Yeah? Cool. And speaking more informally, if we consider this guy, yeah, then this, I'm just going to say in words what I just wrote in maths there. This guy is the sum from n equals 0 up to 9 plus the rest of it, which is this thing. And this thing converges. So as Hussein said, if you just have a few more terms added to your convergence series, obviously it's still going to converge because you're just adding some quantity that is just finite to something where you're taking the limit. It's not going to change anything. Yeah? So we can prove something converges by proving it converges for any n, starting anywhere. So n could be at 3,064,112, whatever, it doesn't matter. If the sum from 3,664 to infinity makes sense, then the sum from n equals 0 to infinity makes sense. Yeah? Everybody good? All right, cool. We'll raise the board. We do some more. I'm also open to doing, let's do question 10. This is another question which, rather than making you compute something, it's asking you to figure something out using some principles. So the question is, which of the following are true? So the first statement is that, let's put it over here. All right, so now this thing is a positive function. Yeah, it's a positive function because sine is always between -1 and 1. Yeah. So what we have is something which is between 1 and 3, right? So look at this. So sine of x plus 2 is always less than 3, and it's always bigger than 1. Yeah? And therefore, this thing, sine of x plus 2 over x to the 3, this is a positive function, and it's always going to be less than 3 over x to the 3. Yeah? So if we put the graph of this guy, sine of x plus 2, what will it do? It will be like 2, and then it'll increase and then decrease like this. It's going to go like this. Yeah? but it's always going to be less than the graph of this thing, at least from 4 onwards. So the graph of this thing is above it. Yeah? So the question of whether or not this thing converges is the question of whether or not the area underneath this graph is ultimately finite. Yeah? As we go off towards infinity. And the answer is yes, it will be finite because the area of this guy is definitely finite, and we know this because we've learned that when we do improper integrals of type 1 and we have a power which is bigger than 1, then it converges. Yeah? So it is the case that we can compare this thing to this thing. The false part of the statement is that this thing diverges. It doesn't diverge, it converges. Which of the following is true? Not this one. This is not true. So, not true, because this integral 4 to infinity sine of x plus 2, x to the 3 dx converges. All right, next statement. This is the next. Look at this statement. This thing diverges in comparison to this thing. Okay, do we believe this? Is this true? Come on, speak up. Yeah. Yep. Keep going. Okay, everything you're saying is correct, but let's identify which part of this stuff is actually wrong. Which part of this is wrong? Come on. Perfect. It is the first part. Excellent. Look at this. This statement is false because exactly as you say, e to the x blows up incredibly quickly as x grows. So 1 over square root of x plus e to the x goes down to 0 incredibly quickly, so we'd expect it to converge. Yeah? Yeah? Because any power of x which is bigger than 1, when we consider 1 over x to that power, that thing converges, and that is going down to 0 so much more slowly than this thing. Yeah? Because x to the p is blowing up so much more slowly than e to the x. E to the x is the monster function that blows up faster than anything we can conceive of. Yeah? Yeah? So this thing will very much converge. Yeah? This will very much converge. And we can see that pretty easily just by comparing it to this thing. Look, square root of x plus e to the x is less than 1 over e to the x, right? Because this thing, yeah, this thing on the bottom is bigger than this thing. Yeah? So this is less than this thing, and this thing we know converges. We can easily calculate this. This is just e to the minus x, right? Yeah? The antiderivative is minus e to the minus x. We calculated. We know this thing converges. Yeah? Give me the thumbs up if that makes sense. Okay, super. So this part of the statement is false. What about this guy here? Does this thing actually diverge or converge? Yes, it's decreasing slowly enough. And what's the key example that tells us that this thing is decreasing slowly enough? 1 over x, right? So we know that 1 over x diverges, yeah? And this guy lives above 1 over x, right? So for any x bigger than 1, so if x is bigger than 1, right, the square root of x is less than x. Yeah? So 1 over x is smaller than the square root of x. This guy lives above it. Yeah? So if the area underneath the graph of 1 over x is infinite, then for sure this thing is infinite, right? And we simply learned that whenever we have the integral 1 over x to the p from 1 to the infinity, and p is between 0 and 1, then this thing diverges. This is the thing that we learned. So the 1 over x is the cutoff, right? If we're underneath 1 over x, we're okay. If p is actually bigger than 1, we're okay. Yeah? But if p is between 0 and 1, then we're not okay, then it won't converge. Yeah? So this guy does diverge. So they're trying to trick you a little bit because they're asking you to conclude something diverges by comparing it to something that diverges, which would be correct if this guy was underneath this guy. but it's not. It's way on top of it, yeah? as you people told me. Yeah? So this is completely false. This is a false statement. They're trying to be tricky with us, but it's a false statement. Yeah? Cool. All right, let's keep going. Next question, similar kind of function. Oh, it's the same function. Yeah, it's the same functions, except now they're rephrasing it. The next question is they say, this thing converges in comparison with this thing. Is that true? Is that a true statement? So the statement is that this thing converges in comparison with this. Is that true? Perfect, perfect. Very, very good. Yeah, this thing does converge, we just discussed, but this thing doesn't converge. Yeah? So we can't compare this thing that converges to something that doesn't converge and then conclude it converges, right? So it is the case that the function 1 over square root of x plus e to the x is underneath this guy, yeah? But this guy does not converge. It has infinite area underneath this graph. So if we have a function who has infinite area underneath this graph, right, and we have a guy that's underneath it, like this, then we can't conclude that the guy underneath it has got finite area underneath this graph just because it's underneath the graph of something that has infinite area, right? If we had finite area of the guy that is above it, then for sure that forces this guy to be finite. But the fact that this guy is infinite and this guy is underneath it means nothing, right? We can't conclude anything from that. Yeah? So hopefully the picture makes that clear. Yeah? Are you with me here? Give me the icon or the thumb. Okay, cool. All right. So this statement is also false. Okay. Next statement. Integral from 4 to infinity 1 over e to the minus x plus x to the 3 diverges in comparison with, so I'm going to abbreviate comparison with just conf dot, with the integral from 4 to infinity of 1 over e to the, I'm wondering if they really mean e to the minus x. Yeah, okay, let's assume that's correct. E to the minus x. All right. Is this true? Is this true? Okay, which part is not true? Say it louder. Yeah, the divergence part. So this thing will indeed not diverge, it will converge. Tell me why. What is making this thing converge? X to the power 3, yeah? So we see that this thing, e to the minus x plus x to the 3, is less than 1 over x to the 3, yeah? And we know that this guy here converges. So this graph is underneath the graph of something that converges, therefore it must converge. So this initial part here is false. Yeah? This initial part here is false. Yeah? What about this thing? Does this thing converge? Does this converge? Because? Perfect, perfect. That's just e to the x, which is blowing up. Yeah? So this thing dramatically fails to converge. Yeah? Cool. All right. I don't know, can't see which one this is. So this is evaluate this integral. Okay, given what we know about improper integrals of type 1, what is your guess about this thing? Do you think it converges or not? Can we make any initial guess? What is this thing most like? But what's the most important term on the bottom? Yeah, the x is way more important than the log, right? Because for very large x is a lot bigger than log of x. So log of x is the slowest growing function we know, being the inverse of e to the x. Yeah? Yeah. So this expression is a lot like 2 over x, but it's a little bit smaller than 2 over x. Yeah? It's a little bit smaller because we also have this log x thing, which is growing. It's growing very slowly. Yeah? Yeah? So this guy, we might look at this and go, okay, well, we know if it was like 1 or 2 over x to the power 1 plus something, like 1.001, then that thing would converge, because that's what we learned. Because it converges whenever we have 1 over x to the p, where p is bigger than 1. Yeah? Yeah? But this guy is going to 0 much more slowly than 1 over x to the power 1.01. Because this log thing is a lot more slowly growing than anything. You see what I mean? Yeah? Because if we had 1 over x to the 1.01, then that's like 1 over x times x to the 0.01, which is like a tiny root power of x. But this tiny root power of x is still growing a lot faster than log. Log is more slowly growing than anything. Yeah? Much more slowly growing than any root power. Yeah? But this guy would be okay. This guy would converge. Yeah? This guy would converge, because we learnt that. Yeah? But this guy, it's not clear. This guy, it's not clear. It's right on the edge of converging or not converging. If it was just 2 over x, it definitely wouldn't converge. Yeah? So this is right on the edge. Yeah? Okay, cool. So our basic rough guide about comparing things to 1 over x isn't going to help us here, because it's so close. It's so close to 1 over x. So we have to compute it. We have to calculate it. So let me put a sentence. So compare to no good, because this guy is bigger. I should say smaller. 1 over x to 1.01 is smaller than this thing. Yeah, so right on the edge. Okay, so we have to compute this. So let's call this thing star. We know what star is. Star is equal to the limit as capital R goes to infinity. If you have to leave, go ahead and leave. And please watch the video for anything else that I cover after you've gone. Okay, so this, oops, squared dx, like this, yeah? And then how are we going to evaluate this? What's a natural thing to do to try and evaluate this? U sub. What am I going to U sub in? What's going to be the U? Yeah, so if I let U be log of x, then du by dx is 1 over x. So du equals dx over x. Yeah? And then this thing we can now change around. So when x is equal to 2, we have log of 2. When x is equal to r, we have log of r, like this. And then we're going to have 2, and this x, this dx over x, is this thing over here. So we're just going to have 2 over u squared du. Yeah? Yeah? And then we're happy, because this thing we can do, let's pull out the 2. It's the limit as r goes to infinity. Log of 2, log of r, and then it's the antiderivative of u to the minus 2, so it's going to be minus u to the minus 1, like this. Oops, I need to put this like this. and this is log and this is log 2. And then what's this? This is, let's put the minus sign outside. So this is the limit as r goes to infinity of log of r to the minus 1 minus log of 2 to the minus 1, like this. Yeah. And as r goes to infinity, log of r does blow up. So log of r to the minus 1 just goes to 0. So then this whole thing is just going to be minus 2 times minus this thing. So it's just going to be 2 over log 2. Yeah. So this thing does converge, and this is equal to the answer. Yeah. Everybody happy? Okay, cool. So this is a kind of a slightly trickier situation because, again, we can't just compare it to 1 over x. We have to evaluate it. But if you look at this thing, most of you saw pretty easily that the u sub is the natural thing. And sure enough, that works. Okay, test question. What if we had this? What if we had 2 over x times log of x, like this, which is just a little bit more slowly growing? Start again. It's a little bit more slowly decreasing. Do you think that would converge? Say it louder. It will diverge, yeah? Because if we do exactly the same trick, then, or exactly the same u sub, then here we'll have u to the minus 1, right? Yeah? Yeah, so you can go through exactly the same steps, but here would have u to the minus 1, which we know diverges, yeah? So this is kind of interesting. So it only just converges. It only just converges. It's just going slowly enough down to 0 that it converges, yeah? In fact, if we think a little bit more, if we have anything here, if we have p, where p is bigger than 1, it will converge. And if p equals 1, it won't converge. Yeah? So this is the most slowly converging, the most on the edge converging type 1 integral we can easily come up with. We could do a log-log type thing, but of the kind of integrals you'll naturally come up, this guy is just as slow as it can possibly go. Yeah? All right, let's do another one. What about this one? Okay, let's just do a couple more quickly, and then let's do office hour. So look at this. Okay, so rather than evaluate, I just want you to tell me if you think it's going to converge or not, and tell me why. Perfect, perfect, perfect. That's, you people are doing great. Yeah. E to the 2x is blowing up a lot faster than x, so this thing, yeah, this thing is a massacre. This thing is so much more slowly growing than this thing that the entire expression will decrease down to 0. So, for example, we know that e to the 2x is a lot bigger than, say, 2x to the power 3 for some x bigger than whatever. Say x bigger than 4 or whatever, yeah? Because exponentials beat polynomials, yeah? So then this expression here is going to be less than x over 2x to the 3, which is 1 over 8, x over x to the 3, which is 1 over 8 times x squared. So it's going to be underneath a function that converges, yeah? So we'd expect it to converge. And what method would we use to evaluate this? It's a classic integration by parts, right? Because if we let this thing be the v prime and we let this thing be the u, then going from v prime to v doesn't make much difference, doesn't make it much worse. Whereas if we differentiate u, we get something better, yeah? So this is a classic integration by parts. Okay, cool. Let's do this guy here. This is c. The integral from 0 to infinity x squared over 9 plus x to the 6 dx. Do you expect it to converge? Why? Why so? Yeah, x to the power 6 is much bigger than x squared. In fact, if we think about this for very large x, then the 9 is kind of unimportant. So this is like this, right? which is just 1 over x to the 4. So morally speaking, we expect this thing to go down to 0 like 1 over x to the 4, and that's going to 0 fast enough. Yeah. So we expect it to converge. Yeah. And in fact, we can do a strict inequality here because this is positive. So this thing is actually less than this thing because just adding 9 to the bottom makes the bottom bigger and therefore the entire expression smaller. Yeah? Cool. So by comparing it to this thing, we know it converges. All right. So knowing that it converges, what method do you want to use to do this? Yes. X to the power 3. Yeah. Because if we do u is equal x to the 3, then du equals 3 x squared dx, right? So du over 3 equals x squared dx. And then we turn this guy, so if we do the integral from 0 to r, then we're going to do integral from 0 to r to the power 3. This x squared dx thing is over here, so let's put the 1 over 3 out here, and then we're going to have 1 over, so x to the 6 is x to the 3 squared, so we're going to have 9 plus u squared du. And then what? What territory is this in now? Trig subterritory. Yeah? Trig subterritory. So we can factor out the 9, and then we're going to have, okay, I don't want to complete this because we have to do office hour. Factor out the 9, and then we have this thing. And we know that 1 over 1 plus, say, x squared, 1 over 1 plus x squared, this thing is what we get when we differentiate arctan, right? So we can pull out the 1 over 9, we can get the antiderivative out of arctan, and we can calculate this integral. Yeah? Cool. All right, so now it's office hour. Stick around if you have any questions. And but finding this as a u sub, if you look back on the strategy for integration, that's one of the list of things, or the first things to try is to try and transform it into something simpler with a u sub. And so that you should try to anticipate this by thinking, okay, I know that anything of the form of 1 over some constant plus something squared I can do because I can transform it into something like this, 1 over 1 plus x squared, and then get it from arctan. So the thought to have is that if instead of having x to the power 6, I had something squared, that would be good. Well, x to the power 6 is x to the power 3 squared. And if I try a u sub with x to the power 3, then I'm going to pick up these x squared dx. So if you've done more u sub type questions, this shouldn't be a particularly difficult u sub. It's kind of an example how this stuff accumulates so that if you shake you on any particular topic, then it's going to come back to bite you, to make things worse for you going forward. So you have to really nail down everything. Even some of these topics may be more interesting or less interesting for you. You've got to be fluent in all of them. It's the sum of the first n terms of the series. So Sn is the sum from n equals 1 to capital N of this guy like this. So if we have positive terms, okay, so this is the first term, this is the second term, this is the third term, and so on. So this is like 1, 2, 3. Then if this guy is from n minus 1 to n, so I'm just going to keep drawing this. Okay, this guy should be smaller. Like this. Then Sn is all of this. It's this block plus 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 this block. Yeah? And the actual infinite sum is the area underneath all of these blocks. Yeah? Yeah? So this thing, if we let n go to infinity, that thing will be more and more like the area underneath all these infinite blocks. Yeah? In some sense. Yeah? And in particular, if this thing tends to some finite limit, then it's reasonable for us to say that the area underneath all of these blocks from 1 to infinity is finite, and it's equal to this. This thing is always less than the area of all of these blocks, going from 1 to infinity. But as we increase n, if it converges to some particular answer, then that thing is the way we can meaningfully give some reasonable quantity to this thing. So n equals 1 to infinity an. This thing only makes sense as the limit of this thing. And the analogous situation is when we do this. So you are much more familiar with integrals, so perhaps this seems less kind of confusing, but this is exactly the same idea, and it's exactly the same picture. So if we take the limit as capital R goes to infinity from 1 to R, f of x, right? This, you've learned that the area underneath the graph from 1 to infinity means what happens as we take the area from 1 to R and just let R get bigger and bigger. And if that tends to something, then that's what we call this. That's what we define it to be. This is the same thing, because now we have blocks, okay? But in the case when we have positive terms, this thing, the meaning of this thing, is just the area of the first n blocks. And if we let n goes to infinity, then that thing, if it comes to some consistent answer, will be the meaning of what is the area underneath all of the blocks. In exactly the same way as we let r tends to infinity, the meaning of what is the area underneath the graph from 1 to infinity is the limit of the integral from 1 to r as r goes to infinity, if that limit exists. Because can you sort of see that the pictures are just really similar? Yeah? Okay, good.